we go through an example of two-dimensional kinematics of projectile motion. This is the Choi, Brown, and Lucy problem. Choi Brown actually does get to kick the football. The initial velocity of the football, vector v0, has a magnitude of 22 meters per second and close to the optimal angle, so 40 degrees above the horizontal. We want to find what's the maximum height the football reaches, how long is it in the air, what's its hang time, call that the time of flight, so t sub TOF. What's the range of the football, so how far along the x coordinate does the football go before it reaches the ground again. We'll start off by filling in our inventory for what things we know, what things we don't know. And it's going to be more lengthy list because we have both the x direction and the y direction. So we have an initial time, initial x coordinate, initial y coordinate. There is a final time, and this is going to be a little more complicated because I'm going to use two different possible final times depending upon which of these questions we're going to address. There is a final x position and a final y position. We also have initial velocities, so vi x, vi y, v final x, then v final y, having two possible values depending on which time I pick, and then acceleration on the x direction, acceleration on the y direction. So that's all my variables. I can pick the initial time to be 0, initial x coordinate to be 0, initial y coordinate to be 0. So it's just saying the football starts off at time 0 at a position x and y equal to 0. X final is what we're going to try to solve for as the range. Y final is one thing we'll solve for as the height. So the maximum height to answer the first question. The final time, we have two values that we're going to use as we go through this. One is going to correspond to reaching the highest point, and then one is going to correspond to the whole time of flight, the total time it's in the air. So time final, I could mean that to be the full time of flight or the time it takes to reach the highest point, which is going to be half of the time of flight. We need to solve for that. The initial velocities, we have enough information to solve for those. The x component is going to be the initial speed times cosine of 40 degrees. And I get that to be 16.9 meters per second. Initial y component of velocity, the initial speed times sine of 40 degrees, that to be 14.1 meters per second. V final x is the same as V initial x. There's no forces acting left or right. So that stays the same. all the way up to the point that it reaches the ground. V final y, I'm going to take it to be 0 when it's at the highest point, and V final y is going to be minus 14.1 meters per second when it returns to starting y initial. So if it was initially going up at 14.1 meters per second, it's going to be going 14.1 meters per second down right before it reaches the ground again. There are no forces acting left or right, so the x component of acceleration is 0. And the y component of acceleration, I picked what my positive directions are to the right and up, so gravity is going to pull the ball down. That's minus 9.81 meters per second squared for that choice of coordinates. All right, so let's answer the first question. Find the maximum height. If I want to find y final without knowing anything about the time yet, I'm going to use our fourth equation of kinematics, but just along the y direction. So v final y squared minus v initial y squared is going to be 2 acceleration along y delta y. And at the highest point, the football is neither going up nor going down, so v final y has to be 0. I want to use this equation to solve for delta y. And that's going to be delta y, y final minus y initial, which we took to be 0, is going to equal minus v initial y component squared over twice ay. And we put in numbers, a minus sign. VIY was 14.1 meters per second, so I'll have that squared. The denominator, I've got 2, and AY is minus 9.81 meters per second squared, and that's going to give me maximum height 10.1 meters. Okay. Next thing I want to solve for is what was the hang time, so what's the total time of flight. To do that, can use the definition of acceleration, so how the velocity along the y direction changes. So v final y is going to equal acceleration along the y direction times delta t, but delta t is equal to t final plus the initial y velocity. At the highest point, that's 0. So we're going to have 0 is equal to v initial y plus acceleration on the y direction times the final time, and the time to reach the highest point. And that's going to give me t final is equal to minus v initial y over the y component of acceleration. So I'm going to have minus 14.1 meters per second divided by minus 9.81 meters per second squared, and that gives me plus 1.44 seconds. So that's the time to reach maximum height. It's going up to the maximum height, and it's going to all go all the way back down to the ground. So the time to get up to the highest point is equal to the time to fall from that highest point back to the ground. So my total time of flight is going to be twice t final. So I'll have, taking into account rounding, 2.87 seconds. All right. The last thing we want to solve is what's the range. So how far does the football go downfield? For that, use a handy little equation. There's no acceleration along the x or y, or no acceleration along the x direction. Displacement along x, which is x final minus x initial. We took that to be 0, is the average velocity, vix plus v final x, times the total time the football was in the air, the time of flight. And this is what we mean by the range. V initial x is equal to v final x, so this is going to be equal to a half of 2 v initial x times the time of flight, and the half and the 2 will cancel out. So that's v initial x times the time of flight. We actually put in numbers. It's going to be 16.9 meters per second times our 2.87 seconds. And that's a pretty hefty kick, 48.5 meters. Not bad. All right, so kinematics with 2 dimensions involved in the motion, you can operate with a set of kinematics equations for y. You'll have a set of kinematics equations for x, and the only thing that connects those two together is time. Time is the same moving along the x direction and along the y direction. But otherwise, no different than a one-dimensional kinematics problem. You have a separate set of kinematics equations for each of your spatial dimensions.